is first, we added these in series. And because it's a capacitor, we added the inverse to get 2 farads, and we drew our condensation here. Then we added these two, where they're in parallel, so we just add them. So we got the 4 farad capacitor here. We used a voltage of 12 volts and this equation for the behavior of the capacitor to get a 48 coulomb charge that's going to be on this system. Because this capacitor that we made right here represents the whole system. So I have to figure out how to spread that 48 coulombs of charge into the system. Now, rather than start the hard way and try to do a proportion, I should just look at this and say, wait a minute, what's the voltage here? I know the voltage, I know the capacitance. So I will just use Q as CV. That's how I multiplied this and got 24 coulombs there. And if there's 24 coulombs on this plate, there must be 24 coulombs on that plate. So then I put the 24 coulombs there. That 24 coulombs, I can combine it with the capacitance to get the 4 volts, which actually makes a lot of sense, because then I'm losing 4 volts at each capacitor. That means the loop rule works, and everything is good. Okay, now, the next level of question that you would receive on this one would be how much power, how much power is used up at each one of these resistors. In that case, you would just use IV, I squared R, or V squared over R to calculate the power at each resistor. For here, we don't talk about power that's consumed in a capacitor. We talk about the potential energy stored, or what is often called PEC. PEC or UC, and that's 1/2 CV squared. So then you could say, how much energy is stored in this capacitor? Well, 1/2 CV squared. V is 4, C is 6, so that's 3 times 16, which is 48. So there are 48 joules of energy stored on that capacitor. And that, please, is it. Questions from the capacitor?